Hi everyone. Thank you very much for the opportunity to be here. My name is Saverio Cambioni. I'm currently a postdoctoral scholar at the California Institute of Technology. And today I'm going to talk about machine learning and in particular how it's an essential tool for doing the next wave of discoveries in small body science. Before doing that, I would like to spend a few words about my background in research, as this is my first SBAG meeting. And I got my PhD from the University of Arizona, indeed working on a thesis on the application of machine learning to planetary sciences. On the right, I put some of the papers that I worked on small bodies. Not all of them treats of or uses machine learning. The one with the red star do, and I will be happy to discuss any of those. If you have any question, please feel free to reach out. So why I got interested in machine learning? This is actually a plot that we saw also this morning. The reason why I got interested in machine learning for small bodies is because we live in a period in which we have a lot of data, and the data collection for small bodies are expanded by orders of magnitudes in the last 2-3 decades. Not only discovery of new asteroids, as plotted here on the right for near-Earth asteroid, but also for physical data of asteroids, like we saw in the previous talks, and a very large spacecraft data set. Just think about like the data returned by OSIRIS-REx, and more laboratory measurements. So all this data is great. I mean, we can do more science, we can do more discoveries. However, they also bring us some challenges. And first of all, as data sets grow, data analysis can also become less tractable. And also data are diverse. We have data from telescopes, and we try to reconcile them with data from spacecraft. So the approach that I explored in my thesis and I'm currently exploring in my research is to use machine learning, intended as the group of algorithms that enable data-driven solution to planetary science problems. What I mean with data-driven is somewhat depicted in this slide. On the left, you see what I call a parent model. So it could be like a model that you like use for modeling a process for asteroids. And you can write down the equation of physics for this model. But most of the models are typically have a longer runtime. So they take a long time to given an input X to give an answer Y. And instead of having using this parent model, which could be also, for instance, measurements from an experiment in the lab in which you have an input and you measure the output, you can think of taking an example of examples X and Y, and to train a machine learning algorithm on it. In the machine learning algorithm per se doesn't know the equation of physics, but knows how to map the input X into the outcome Y. The advantage that you get with this is that you get a model, which I call a surrogate model, that is very fast and is accurate within a known level of accuracy of the parent model. You're also able to get better and better as you provide more data because it's fast, is invertible statistically, and also can be used for different applications, is versatile. There are some challenges, of course. Machine learning is not all easy, and it is not magic. It doesn't solve all the problems. For sure, like this surrogate model does prediction, but it doesn't test the physical accuracy of that prediction. In a certain sense, if you have a model, it doesn't do any better than that model. It's a bit time consuming to prepare the data, and also there is a problem of interpretability. And to go through these advantages and challenges, today I'm going to talk about 2 case studies that I did in my research. The first one is about the production of regolith on asteroids and how you can characterize that using machine learning. In particular, the question is how can we use measurements of emitted infrared fluxes to distinguish rocks from fine regolith. With fine regolith here, I refer to sub-centimeters particles. The traditional approach is, which defines a bit our parent model, is to model the thermal emission in terms of roughness and a single value of thermal inertia, which is a resistance of material to change its temperature, which then gets typically interpreted as a particle grain size. However, the interpretation of low thermal inertia measurements of low thermal inertia and particle grain size has been proved to be a bit problematic, for instance, when we got Bennu and Ryugo, which show clearly a mismatch between low thermal inertia and abundance of fine regolith. So in the meanwhile, we thought to develop a machine learning approach, mostly to make the exploration of the parameter space of fine regolith and rock emission feasible to be explored computationally. And indeed, we trained the machine to recognize the combination of emission by rock and regolith, combine them linearly, and then fit the model to the data. And derive what we call rock abundance, which is this linear combination factor between the fluxes of regolith and rock. We applied this approach to asteroid Itokawa. In particular, we used 30 ground-based observation, which are disk integrated for Itokawa. And we used the machine learning model in a statistical way, in the sense that we statistically invert it. And this gives probability distributions that you can see here on the right. The one I would like to draw your attention to are the one for thermal inertia of the regolith, rock abundance and thermal inertia of the rock. The peak value corresponds to the most probable value for the surface. If you take this value of thermal inertia, it converts to centimeter size particles. The rock abundance is in the order of 85–84%, which means that the regolith abundance is in the order of 20%. And these two findings actually were nicely in agreement with what Hayabusa found, but once getting to the asteroid. And I would like to remind that our work was using ground-based observation. On top of that, we also find that the rock thermal inertia is lower than what you would expect, given the analog for a meteorite analog for Itokawa, like chondrites, indicating that rocks could be fractured. Now here the challenge was with the machine learning algorithm. It's great that it can provide insights that were not available before. However, how can we test the reliability of these results without having then basically a spacecraft going there and providing ground truth? And these results were published in this paper on Icarus in 2019. We are currently working on data for Bennu. The second case study that I would like to talk today still speaks about, in a certain way, distribution of regolith over the surface of asteroids, and in particular wants to characterize and find the smooth terrains on the surface of the asteroids. We did this search for Bennu, in particular because we wanted to see if there was a sampleable surface in the early phases of the mission. Smooth terrains are typically associated with fine regolith, again sub-centimeters, and this is something that comes, for instance, from Itokawa observation. The traditional approach, which again define our parent model, is that we have team members looking at spacecraft images and flagging areas that appears to be smooth and where abundant consolidated material is present, but this is based on the team member experience. And then what we wanted to do is to take some of these images that were labeled by the team members and train a machine to associate the textures that were present in these asteroid images for Bennu to the presence or the absence of smooth terrains. Once this algorithm was trained to do so, we deployed it to the entire surface as an alternative approach to look for potentially sampleable areas. One interesting point about this work is that we customized the texture cam algorithm that was developed at JPL for looking for different rock types and textures on Mars. The result is here, is this map. Will guide you through the different symbols. This is a map of Bennu, 5 centimeters per pixel. The circles are the areas that were found by the team members. As you can see, they are kind of like concentrated in the north hemisphere. The patched areas, these areas that I indicated with my cursor, are that appear red to me, like pinkish, are the areas of smooth terrains that were found by the machine learning algorithm. And the red red circle here are areas of boulders that we covered, because we later found that the algorithm, if it was finding an area which was covered, for instance, by a smooth boulder, it was actually classifying that boulder as smooth. But this, of course, was not an area where you would want to sample. An interesting home of this work is not only we found new areas that were considered for sampling, but also we found that the team members got tired, starting from the North Pole, going toward the south, of looking for areas, because actually the machine learning algorithm didn't find any asymmetry north-south, while the team members did. So to wrap up these two case studies, the advantages of machine learning is that, of course, it manages well big data. You have this large data set of images, and you can find like smooth areas, for instance. It's data-driven in the sense that we can, what we can do is to protect against overfitting the data and not introduce physical assumptions. It's invertible because it's very fast algorithms, so you can do statistical analysis with it, and is also versatile. In particular, for instance, the case for that software that we customized for searching for smooth terrains. The challenges of machine learning is that, as I mentioned before, it doesn't assess the physical accuracy of prediction per se, so it needs like the expert behind to recognize if a prediction is physically accurate or not. It could be time-consuming to prepare the data, and then there is a problem of interpretability. The surrogate model, the machine learning model, can be perceived somewhat as a black box sometimes, and this is a very important point of current research. I will conclude with this plot, which was in my thesis. Number of publications per year in Earth and planetary science discussing machine learning as a function of time. This is an estimate. You can see that the trend is also exponential in the last 20, 30 years, as it was the exponential increase of our data, but we are only totaling of 3.6% in 2020. So given the potentialities and also the need to study what are the limits and challenges of machine learning, I think we need to invest in machine learning. Considering, for instance, certifying the PDART program, creating new data analysis programs, incentivizing, this is something I didn't talk about today, but incentivizing the use of small-sat for or low-cost mission for increasing the technology readiness level of the autonomous exploration, more machine learning in courses, undergraduate and graduate courses level. And last but not least, there have been some recent interesting work using machine learning to study the demographics in the planetary science population, or also like biases, for instance, citation count. This citation count was a paper by Kaplan et al. In Nature Astronomy. Thank you very much for your attention, and I think I left a few minutes for questions and discussions, if anyone wants to.
Thank you. We have a minute to ask questions, or please use the chat feature to type any questions you might have, or use the email address to contact the speaker.